There is a profound irony at the heart of Japanese metallurgy. The most legendary blade in human history. The one that defined the identity of an entire civilization and became a cultural symbol recognized across the entire modern world, was not born from the purest steel that engineering could produce. It was born from controlled imperfection, from a process that modern industry would flag as a quality failure before the metal even cooled. And it all begins with clay. To understand why the Japanese sword remains, to this day, a subject of serious academic study in material science and engineering departments around the world, you first need to abandon everything you think you know about what makes a good material. The instinct of modern manufacturing is to eliminate variables. To control every input, purify every compound, and achieve the most predictable, reproducible output possible. That instinct built skyscrapers, aircraft carriers, and surgical tools.
But it cannot build a katana. Not the real one.
Not the one that has been tested across centuries of use and found, repeatedly, to perform in ways that make metallurgists reach for their notebooks. The process starts not with metal, but with earth. The tatara is not a furnace in the sense that modern engineers would recognize. It is more accurately described as a disposable chemical reactor. A structure built with the full understanding that it will be destroyed at the end of the process. The word itself refers to the traditional Japanese foot bellows smelting system, a technology that was refined over roughly 1,000 years, before it reached the form that produced the blades now housed in museums and studied in laboratories. The construction of a tatara is its own discipline. Specific layers of clay and ash are assembled in a precise sequence, and the resulting structure must then undergo a slow, deliberate drying process before any smelting begins. That drying phase is not ceremony. It is structural engineering. Clay contains water at the molecular level, and when clay is exposed to sudden intense heat before that water has been driven out gradually, the steam that forms inside the material has nowhere to go. It expands violently and tears the structure apart from within. A tatara that cracks before the smelting is complete is not just a setback. Depending on the stage of the process, it can mean the loss of days of continuous labor by an entire team of workers. The patience demanded by the drying phase is not a spiritual virtue cultivated for its own sake. It is a hard technical requirement, written into the material itself. What separates the tatara from a modern steel-lined industrial furnace is precisely the characteristic that, at first glance, appears to be a weakness. Clay is not a neutral container. It does not simply hold the heat and the charge at a fixed distance from each other. It participates in the process. Because clay is a thermally imperfect and naturally variable insulator, different regions inside the same smelting space maintain different temperatures simultaneously. The center burns differently from the edges. The bottom accumulates heat in a different pattern from the top. The walls absorb and radiate at rates that shift, as the clay itself undergoes chemical changes during the firing. In an industrial furnace designed around uniformity, this kind of thermal variation would be considered a flaw to be corrected. In the tatara, it is the most valuable characteristic of the entire system. This is the first layer of the paradox that defines Japanese swordmaking, and it runs much deeper than most popular accounts acknowledge. The central smelting process lasts roughly 3 days of continuous operation. This is not an arbitrary tradition preserved out of cultural inertia. It is the minimum duration required for indirect reduction to proceed correctly, given the specific inputs and the constraints of the clay furnace. Throughout that entire period, without interruption, through day and night, operators feed 2 materials into the fire at regular intervals. The first is setetsu, a fine iron-bearing sand extracted from riverbeds in the Chugoku region of western Japan. The second is charcoal, specifically charcoal produced from pine, which burns at the temperatures required while maintaining the carbon chemistry the process depends on. The role of charcoal here is almost universally misunderstood in popular discussions, and the misunderstanding leads to a fundamental confusion about what the process actually achieves. Charcoal is not simply a fuel that generates heat. It is a reducing agent. As it burns, it produces carbon monoxide, and that carbon monoxide reacts with the iron oxides present in the setetsu sand, stripping away the oxygen that keeps the iron locked in its mineral form. What remains is metallic iron. At the same time, some of the carbon itself is absorbed into the iron at varying rates, depending on local temperature position within the furnace and the flow of air from the bellows. The continuous feeding rhythm is not ritual. It is process control, maintaining the chemical environment inside the furnace within the range that allows this absorption to continue at the right pace. After roughly 3 days of uninterrupted work, the clay structure is broken open and the result is extracted. What emerges is called tamahagane, which translates approximately as jewel steel, though the name refers more to its preciousness than to any visual quality.
The block is not uniform.
It contains regions of low-carbon steel that are soft and ductile, regions of high-carbon steel that are hard and brittle, and everything in between, all within the same mass of metal. To a modern quality control inspector, this would represent a production failure. To the Japanese swordsmith, this heterogeneity is the entire point. Here, the science becomes genuinely surprising to anyone encountering it for the first time. Modern industrial steels are remarkably clean. The metallurgical purity achieved by contemporary steelmaking processes is extraordinary by historical standards. Composition is controlled to fractional percentages. Crystal structure is managed through precise thermal cycles. Inclusions and impurities are minimized and eliminated. This level of control produces steel that performs with extraordinary predictability in applications where uniformity matters. Structural beams, vehicle chassis, machine components. But when researchers began examining historical Japanese blades under electron microscopes and comparing their microstructure to modern steels, they found something unexpected. The 3-day smelting process did not just create carbon variation. It also generated fine silicate inclusions, distributed throughout the metal. These microscopic particles, which modern steelmaking works hard to eliminate, turned out to be a structural feature rather than a defect. When the swordsmith subsequently folds and forges the tamahagane, working it repeatedly across hundreds of individual hammer blows, those inclusions reorganize into ultra-thin layers distributed through the metal's structure. The result is a material that behaves according to principles almost identical to those behind modern fiber-reinforced composites, including carbon fiber. When a crack initiates in the blade and attempts to propagate, it encounters these internal boundaries. The crack deflects, divides, and dissipates, rather than running clean through the material. The blade resists fracture not because it is monolithically tough, but because its internal architecture interrupts the failure mechanism at the microscale. This is what material scientists mean when they describe the structure as a natural composite. And it is exactly the quality that disappears when the production process is made too clean. There is an additional dimension to the smelting science that rarely receives attention in popular accounts of Japanese swordmaking. The bellows, the large foot-operated or hand-operated air pumps that drive combustion in the tatara, are not simply breathing apparatus for the fire. The rhythm and volume of air being pushed into the furnace directly controls the oxidation state of the chemical environment inside the clay chamber. Too much oxygen, and the iron re-oxidizes rather than reducing. Too little, and the temperature drops below the range required for carbon absorption. The operators managing the bellows across 3 continuous days were performing a form of process chemistry that they understood empirically, long before anyone had the vocabulary of carbon chemistry to describe it. They knew what the flame should look like, what the sound of the fire should tell them, what the color of the exhaust gases meant about what was happening inside the clay. That knowledge was accumulated across generations, and transmitted through direct apprenticeship, not through written formulas. A curiosity worth noting here is that the tatara process consumed enormous quantities of charcoal, and by extension, enormous quantities of timber. Historical records from the smelting regions of Japan document significant deforestation driven by the demand for iron production. What makes this particularly interesting is that the communities involved developed sophisticated reforestation practices, specifically to sustain the raw material supply for smelting, effectively creating managed timber cycles tied to the production calendar of the ironworks. The environmental management system and the metallurgical system were deeply intertwined, in ways that only became visible when researchers began looking at the land use records alongside the production records. A civilization that needed iron learned to grow the forest that fed the fire that made the steel. But returning to the metal itself, the work of the swordsmith begins where the tatara ends. The tamahagane is broken apart and sorted. The swordsmith examines each piece, reading the metal by its texture and the way it responds to the hammer, identifying the regions of higher and lower carbon content. These pieces are then selected, arranged, and forged into a composite structure that uses the different properties of different carbon levels intentionally. The hard high-carbon steel goes where hardness is needed. The softer low-carbon material goes where flexibility and impact absorption are required. The folding process that follows is not about creating layers for their own sake. It is about refining the grain structure, distributing the carbon more evenly within each chosen region, and aligning the silicate inclusions into the fibrous architecture that gives the blade its fracture resistance. The number of folds in a traditional blade is often cited in popular sources as a marker of quality, but this deserves careful qualification. Excessive folding beyond what the material requires actually begins to reduce carbon content through oxidation, weakening the steel rather than improving it. The swordsmith's skill lies in knowing when to stop, in reading the metal, rather than following a formula. This is another domain where the tactile, observational knowledge of a trained craftsperson outperforms a fixed procedure. The blade does not follow a recipe. It follows a conversation between the smith and the steel. The culmination of everything, however, is neither the furnace nor the forging. It is the moment of selective hardening. Before the final heat treatment, the swordsmith covers the spine of the blade with a thick application of a clay mixture. The cutting edge receives either no coating, or a very thin layer. The specific composition of that clay mixture, the ratio of clay to ash to other materials, was one of the most closely guarded pieces of knowledge in each swordsmithing tradition. Different schools developed different formulas across centuries, and the precise composition influenced not just the hardness profile of the blade, but the shape and character of the visible transition line that would later appear on the steel surface. When the clay-coated blade is heated to the correct temperature, and then plunged into water, what happens in the following seconds is one of the most elegant transformations that materials science can document. The cutting edge, with little or no insulation, loses its heat almost instantly. The iron crystal structure at the edge has no time to reorganize gradually. It is frozen into a phase called martensite, a body-centered tetragonal crystal structure that forms only when high-carbon steel is cooled faster than the carbon atoms can escape or rearrange. Martensite is extremely hard, approaching the hardness of certain ceramics, and it is responsible for the cutting ability of the blade. The spine, insulated by the thick clay layer, cools slowly. Its crystal structure shifts into a phase called perlite, a lamellar mixture of ferrite and cementite that is far tougher and more ductile than martensite. The two phases coexist within the same continuous piece of metal, joined at a transition zone that is visible to the naked eye as the hamon, the distinctive wavy line that runs along the blade and is one of the most recognized visual features of the Japanese sword. The hamon is not decoration. It is the boundary between two fundamentally different materials that happen to share the same molecular iron backbone. It is the swordsmith's signature, written in crystal structure. An industrial furnace that heats uniformly cannot reproduce this transition by the nature of its design. Differential hardening of this kind requires differential insulation applied by hand, varied in thickness across the length of the blade, according to the judgment of someone who has spent years developing the ability to read the metal's responses. Automated thermal processing can approximate it, and modern metallurgists have successfully replicated the mechanical properties through other methods. But the specific combination of the composite silicate structure from the tamahagane, the forging discipline, and the selective quenching from clay coating, produces a profile of mechanical properties that remains a benchmark in the study of materials that must simultaneously resist fracture and maintain a sharp edge under real cutting conditions. One detail that often surprises people encountering this subject through a technical lens is the role of water temperature in the quenching step. The same blade quenched in cold water versus water held at a higher temperature produces different results in the crystal structure at the edge. Smiths in different traditions and different climates developed quenching protocols adjusted to local conditions, including the specific water sources available to them. The mineral content of the water, not just its temperature, influenced the result. This was discovered empirically across centuries of practice, before anyone understood the thermodynamic and crystallographic reasons for the variation. The smith knew the answer long before science knew the question. The tatara itself, the clay furnace that begins everything, is destroyed at the end of each smelt. The clay walls are broken apart to extract the bloom. The knowledge of how to build the next one correctly, how to layer the materials, how to manage the drying, how to read the furnace's behavior across 3 days of continuous operation, lives in the people who have done it before. There is no manual that substitutes for that. The most detailed written accounts of the process still require an experienced practitioner to interpret and apply correctly.
The furnace dies. The knowledge must not.
What the entire tradition of Japanese sword-making ultimately demonstrates, viewed through the lens of materials science, is that optimization is always optimization toward a specific goal. Modern industrial metallurgy has achieved things that would have been literally inconceivable to a 10th century Japanese ironworker. But it optimized for uniformity, scalability, and predictability, because those are the qualities that industrial civilization requires at scale. The tatara optimized for a particular mechanical relationship between hardness, toughness, and fracture resistance, in a blade-shaped object subjected to the specific stresses of sword use. The impurities were not failures of the process.
They were the process.
The heterogeneity was not a limitation of the technology.
It was the technology.
The clay furnace was designed to be thrown away. The steel it produced in 3 days of continuous fire was designed to last for centuries. In the ruins of the disposable reactor, the swordsmith found a material that no perfectly controlled, perfectly clean industrial process has fully replicated, not because the engineering is beyond modern capability, but because modern engineering, by design, looks for something different when it decides what perfect means.
Historical and technical note. The production of tamahagane via the traditional clay furnace, known as the tatara, is a process strictly preserved and monitored by the NBTHK, the Society for the Preservation of Japanese Art Swords. This text explains the metallurgical principles, such as heterogeneous carbon distribution and selective quenching, that allow this traditional method to produce composite material properties that modern industrial homogenization often struggles to replicate.